Hello, good afternoon once again. My today's talk will be using parallel robot for pedagogy in robotics. So many years after 5 to 6 decades of development of parallel robots, both serial robots and parallel robots they came in together. When Angelberger and Devil gave serial robots, parallel robot also got into almost similar time by Stewart. Both of them found its trajectory almost in same time domain. However, because of the complexity, this didn't find much place in academics. Because of probably the mathematical complexity does it have when you start trying to control this type of robots. Okay, so my request today will be to don't get off too much by the complexity, because given the time and the resources that we have now, and the test book, the documentation, those are available these days. I think parallel robots can also get into picture. However, with time, maybe each and every institute of India haven't evolved that much, but what I see, the things are available, know-how is there in India. There are several robotists in India who are already working into parallel domain. You take as an example how this finds a new place in the market by just observing that KUKA recently has launched one of its robot Delta variant of parallel robot recently in February this year, which has just came into the market. Looking at that, you can imagine such a big company has evolved, and they have recently got into Delta because they must have seen some interest into its marketing aspect. Maybe industry has started evolving already in India, which has gone into parallel robots domain. So my talk today would be more focused on how to get into parallel robots in academics, how teachers can start using parallel robots to teach the robotics their students. Okay, so here I go. So the talk today would include a brief introduction what a parallel robot is in comparison to the serial robot. What may they may already be very much familiar through different books they might have gone through during their standard curriculum or through different resources. Some applications of parallel robot to prove its edge, that it is, yes, it is almost as good as a serial robot. Kinematics of 6 UPS parallel robot, which is commonly known as a Stewart platform or a Stewart-Gough platform, that is named after the scientist who has invented that. And video and media tour of a typical racing car simulator that was developed in my lab, and I'll tell you the intrinsic how it takes to develop such a simulator. Once you will see that, you will definitely find some interest in that. Kinematics of 6 RSS parallel platform, that is again a parallel platform which is of a different variant, a little different, but yes, it is also a parallel robot that I have also developed, and it has now seen the market also. So I'll show some demonstration videos which shows some of the applications what a parallel robot can do, how you can use this as an alternative to serial robots while you teach robotics. So pedagogy in robotics using parallel robot, that is my prime thing what I want to focus upon today as an alternative and beyond. Means you don't just see things which you were doing since long time, you can do much beyond with this. Serial robots and parallel robots. Technically, it needs a special attention because these robots are most widely used robots in the industry. The principles involved in understanding the physics of these robots are quite similar, and it becomes more mathematical as we move from serial to parallel robot. I'll discuss why these robots are so special by understanding its structural differences, advantages, disadvantages, and few of its applications. So let us start. Serial robots are most widely used class of the robots in the industry today. They are simple, easy to use, easy to understand, and easy to program these robots. It has a very good balance between its reach, to a distance which is commonly used in the industry, and its payload capacity. It offers a wide range of payload ranging from a very smaller ones that are commonly used in electronic industry to a huge ones that are used in case of any automobile industries. The video shows various motions that a six-off robot can offer, namely 3 Cartesian translations and 3 rotations in 3 orthogonal directions. These facilitate point-to-point motion, commonly known as PTP motions, which are most commonly used for pick and place tasks like palletizing or moving an object on and off from any moving conveyor. Most of the paths that such applications require are primitive motion tasks, which are in combination of linear or circular motions. And interpolated spline motions are most advanced motion that these robots can make. The applications include welding, painting, material handling, etc. A special and advanced tasks include compliant motion tasks that includes 4 stalk sensor, as in case of material handling using 2 or more robots in collaboration, or any surface finishing task. Serial robots can also be programmed by directly feeding the joint motion trajectories. Each of the joint motion would create a circular arc in space. However, it is difficult to estimate the tool path in such motions. It requires a good amount of experience and proficiency in robot programming skills while using such advanced programming approach. It offers some special advantages. It is used to configure axis-specific workspaces by limiting some specific joint angular motion. This restricts the robot entering into probable areas of collision with the surrounding objects in the robot workspace. The approach of motion restriction for safety against collision can also be achieved using Cartesian workspace limiting. Specifying motion through joint space trajectories become quite useful if the robot end effector passes through any singular positions. Parallel robots. One of the most popular variant of these robots are 3 degrees of freedom delta robot. The applications include pick and place tasks, 3D printing, medical robots, or any gaming platform. The demonstration video here shows a 6 degrees of freedom robot that is popularly known as 6RSS, Revolute Spherical Parallel Robot, that is in Zamanov configuration. It shows 3 translation and 3 rotation motion of the top platform in Cartesian workspace. These robots have very high power to weight ratio. These can be extremely fast and yet precise. These robots are comprised of complex mechanisms. It requires high-end controllers because of its perplexed kinematic and dynamic solutions, and to move smoothly through singularities that exist in its workspace. It has all the capabilities that a serial robot can have. However, it has relatively small functional workspace. Using joint space trajectory for this type of robot is far too complex to be used even by an expert user. Applications of parallel robot. So one of the biggest application which is long back evolved, and it was parallelly rising along with serial robot applications are simulators. Why? Because that forms it gives you a very good platform. It gives you a very good platform where you can put your things on top of a platform, and that platform can give you all sorts of motion: roll, pitch, yaw, heave, okay, and sideways motions. Okay, all the motions can be given easily, and at the same time it can carry huge weight. A person, maybe the whole of the container where you want to make different simulators, so it can take a big amount of weight in a no time and doesn't require much space. Footprint is not much. Okay, so flight simulator mostly was very common, and various gaming engines, they support integrating to these type of simulators: naval simulators, automobile simulators, mainly in the mining trucks what we people normally use. We have huge trucks which gets into open cast mines, and those trucks are as big size as 10 times of a standard truck that you see. So these are very big, so it is very difficult to train the drivers of these trucks. So we normally prefer training them on the simulator, and again it finds a good application of parallel robot. And I have seen in the railway training center also, they train their drivers on these type of simulators which has parallel robot behind. Okay, so moving giant telescope, the application is again very common because you need a precise motion for these telescopes to move on. So what happens, let us say you just tilt by a half a degree error here, so long distances that can be a huge diversion from the actual thing that you want to see. So these robots, these type of parallel manipulators, they handle such things in quite precision, and it can carry the weight of huge telescopes also. The advantages which are intrinsic to parallel robots are very good explored in such applications. Pick and place in food industry, packaging, agro industries, mainly delta version. I'll show you some video of delta version also. So what it does, basically it is a 3 degree of freedom robot which is widely used in industry today. So they are precise and very fast, exceptionally fast as compared to any serial robot, and it can pick up and place in no time. Okay, mostly during in electronic industry this finds its place, and sometimes even in food industry to move things from the conveyor and to the conveyor. Medical robot and surgery, again the requirement is same, you have to be precise, you have to be very precise, and you don't need to carry huge weight here though. So but this helps you doing such surgeries in no time. And yes, serial robot also finds its place. So in case of medical, it is a combination of serial and parallel. Serial robot gives you a huge workspace where you can go, and at the end you may have a micro manipulator which does a surgery, maybe ocular surgery or a brain surgery, as it is shown in the figure. 3D printing is a wide application of parallel robot. You must have seen few 3D printer which are based on Delta 3D printer, which is 3P type of actuators, 3 prismatic joints which are there on the sides as it is shown in the figure. So next is micro manipulation, as I have said. Maybe even if you are having a huge serial robot which can have a huge workspace, but what happens at the end, it may not be that precise as compared to a parallel robot. So what it does, it carries a parallel robot on top of a serial robot where it can have precise motion at the end. You reach there and then you do precise manipulation. So most of the applications where a serial robot can go, with some exception in workspace and reach requirement, definitely parallel robot can also be applied. So why am I stressing so much upon parallel robot? Because in same space you can get more power. So power by weight ratio for this type of robots are little more. Okay, so that is one of the advantage, and in the lab you can have some advanced studies which serial robot may not be that capable of giving those knowledge to your students. So kinematics of standard 6 UPS. UPS here it means universal joint, that is a type of joint which is there in this type of robot. I'll show you some picture. And prismatic joint and spherical joint. Universal joint is a 2 degree of freedom joint with two axes intersecting to each other. It's a standard universal joint. Prismatic is just like a hydraulic ram which you see in earth moving vehicles, and spherical joints are just like your this joint which can have 3 degrees of freedom in a single place, just like a ball socket joint. So it is a spherical joint. This type of platform is popularly known as Stewart or Stewart-Gough platform, sometimes even by Hexapods. It looks like this. So what you see here is something like a spherical joint here. Here you will have universal joint. This becomes a prismatic joint. So you have all 6 of these all 6 will move simultaneously to give the top platform, this orange one, some motion. Okay, it can have roll, it can have pitch. So roll, pitch, yaw motion. Roll is rotating about one axis, pitch is rotating about another orthogonal axis, yaw is a rotation about the axis which is perpendicular to both of the former ones. Okay, so that is yaw. So and displacement in all three directions are also possible. So this is a kinematic diagram of the same. Okay, this is the kinematic diagram of the same, where you have actuators placed at B, B, B. All the B's represent 1 to 6. Those are basically actuators where they are, and then top of the actuators are connected to P's platform, that is P1, P2, P3, P4, P5, P6, and it is given by the location of the top platform is given by the location of the top platform center with respect to base platform center. So it may have a vector which is connecting the bottom to the top. So that basically tells you the position of top platform, and rotation of the top platform with respect to the base can be given by roll, that is rotation about y axis, pitch, that is rotation about x axis, and yaw, that is rotation about z axis. So these axes about which top platforms are rotating are called base axes. Okay, so we'll move ahead with the kinematics now. This is simple vector algebra, need not to worry about. This is very simple, which I will tell you just now. You will be surprised that if it was so simple, why didn't it evolve so easily over the years? So yes, it didn't evolve, that is what is the surprise, but now it has started getting in. And then not only that, yes, there are some complicated mathematics which are there once you start doing forward kinematics, that I will talk about later, and some singularities which are there in its workspace. So those are the reasons, not this one. So this is very simple. So it is just a vector algebra. Let us say you have top platform location, you have a top platform location given by OP, that is the position vector T. So this is T, and the points where your actuators are connected, top platform actuators where they are connected, that those are connected through vectors which are known as PI. PIs are small position vectors. So you know already the locations of PI, because those are not going to change when the platform moves. With respect to its own frame, it is going to remain there. So all PIs are known beforehand. So what you want to do here, I want to do inverse kinematics. So given, let us say I want to go to a particular place in particular orientation, yes. So in that case, what I already know is the top platform points. Let us show you some with an additional figure. So let us say this is your figure. Okay, so these are some of the points, orange ones, okay, where you have different actuators which are there, and top platform is basically these points. So this is a hexagon in shape, and what you have additionally here is these are the points where these actuators are connected. So this is what I mean. So if I want to go to any place, okay, so what additionally I know with respect to this point, these points, all the top platform points are known. So with respect to base, if I turn this, okay, so this platform turns or moves, and all the 6 point with respect to base changes, not with respect to the top platform point, center point. Okay, so this is what is used here. This is what is used here. So provided we know the orientation of top platform, we can directly calculate the rotation matrix for that. If you multiply this position vector with that rotation matrix, what do you get? You get the orientation, this vector basically in terms of O, that is the base platform. So you already know this T vector. This is the position vector of the top platform. This is the input, because you know where you want to go, so that becomes an input. You already know what is the orientation, so you know this matrix, rotation matrix of O with respect to the platform with respect to the base. So multiplied by pi, that is the this vector. So if you multiply that, you get this vector in this frame. So effectively you know this and this. So now what you can know is qi's. This vector, just the vector sum of first two will give you qi. Now additionally, what else you know? You also know where your actuators are located with respect to the base frame. Why? Because that also is not going to change with the time. Okay, they will remain where they are. Whatever be the displacements of these, that is going to remain there. So these BIs are well known beforehand. That is the fixed part of this robot. Again, doing the vector sum, you want to extract what will be the extension of this prismatic links, basically these links. So you want to know the LIs, these lengths. So Qi minus Bi would give you Li. So effectively what you have calculated is this. Using this equation, you can easily obtain the length of the prismatic joint. Let us say it was already having some length. So now you have calculated a new length based on the new orientation and position of the top platform. So difference of those two will give you the displacement that you have to give in order to go to that particular new position. So this is what is the simple mathematics behind. So you can take these type of platform anywhere in space. Okay, any orientation, any position can be given. Okay, so the position of the top platform Ti is position vector of the top platform center with respect to base platform center. As I have said, again orientation is defined by the roll, pitch, yaw angles given by roll, pitch and yaw angles. So taking rotation matrices product, you can simply get this. I would expect a few familiarization of you all with the standard transformation matrix. Maybe computer graphics people know all this, or fundamentals of robotics, that is first two chapters, you know this. So it is nothing but simple rotation matrix. So they can simply be multiplied, 1 over the becomes an operator. Multiply with that, a set of point can be transformed in the space with respect to the base frame. Okay, that is the reference frame. Okay, so I'll show you some example of this type of platform now. So this should be of good interest for you. Okay, so this is a 6-DOF racing simulator on the GOG Stewart platform. You see this, this is what I meant by being prismatic. Those So so this is just the structure of one of the parallel platform which might have been of quite interest for you. Uh, So what different configurations a parallel robot can be of? It can have prismatic joints, it can also have rotary joints. So rotary joints can be of different configuration. So it can be of hunt type as it is shown in this figure A. Figure B shows a similar one which is a hexa configuration when you have rotary actuators which are radially there. Okay, so it rotates in a plane which is passing near to this that is parallel to the diameter line, okay, parallel to the diameter line, protruding radially outwards, so it moves. Okay, in this case it is very much similar to the one that I have shown you just now, this one, where you have rotary actuators which are fitted like this. Okay, that is the Zamanov configuration, and you also can have a hunt configuration as shown in the first figure. So let us work on one of them, that is the Zamanov configuration, Kinematics 6 RSS parallel robot. So again, now it is just an extension of, I won't go too much into the mathematics of this. However, it is not very complex, but still in order to finish in time, I will just give you some philosophy of that. So now that you already know this distance, okay, Li through 6 UPS platform, Stewart platform, you just calculated this length for any configuration of top platform. Okay, so if you know Li, that is the length, it was basically in this frame. So Li you knew. Now it is just made up of two links, two links. Okay, so it has what? It has two links. Uh, First one is this one, yes. So first link is an orange colored link. Okay, this is the orange link, and you have a second link. Okay, so it becomes over here, it is as I have said, it is uh, R, that is revolute joint, planar, S, that is spherical joint, and you have another spherical joint which is over here. So R, S, S, revolute, spherical, spherical. So it becomes it seems it is a two link robot, but effectively it is three, because this is first link. You have 2 degrees of freedom here, so it lets you move in two axes. So basically the second link is of 0 length, and then third link. Okay, so effectively it will be a 3 link robot, but yes, it looks like a 2 link robot. So each of these manipulators, each of these, why it is called parallel? Because this is a top platform which is connected by so many serial connectors. Okay, so one of the advantage of having such parallel robot, when you play lawn tennis, okay, how do you play? Some normally you play with the single hand because you have to reach more. It gives you maximum workspace, you reach more. Okay, but when the ball comes too much on the front, okay, you have to use your power, so you hold the racket with both of your hands. Okay, so in that case what happens, you get more power but lesser reach. Okay, so that becomes a parallel manipulator. When you hold both the hands together and handle your manipulator, okay, handle your racket, it becomes a parallel manipulator. Got it? So this is just an example. So as long as it is single handedly done, so it is a serial robot, but when you hold like this, it becomes a parallel manipulator. So the again coming to this, so all the manipulators, all the serial manipulators are handling this top platform simultaneously. Doing in this way, it basically makes this platform very precise. In case of serial robot, what used to happen, so let us say you have this type of robot, there is some error here, some error here, some error here at the end. Okay, if it is like this, so even with a very small displacement error over here, what will happen? With very small displacement over here, very small error over here, error gets accumulated one by one, and for a small displacement you see a large deflection over here. Okay, so that is what is the problem with this type of manipulator, serial manipulator. So error gets accumulated. So forgetting that now, let us come to our point. So what we intended to do here, now that you know the position of this top platform pi, I just have to do inverse kinematics of this so as to know the bottom angle. So again, you once you know the top platform location, what additionally you can do, you can solve for the each of the individual linkages, and you get the angle of these bottom joints. So once that goes to its place, everything becomes constrained and it reaches there. So there are 6 outputs and total 6 actuator angles as inputs. If it is a 6 degrees of freedom robot, this is a 6 degrees of freedom robot. So fixing just the angles which are here at the base actuators, it fixes whole of this platform. You don't have to worry about what will happen to this free spherical joint. Just like the case this one, what happens? Yeah, this is what is a 4-bar mechanism. So this is how many degrees of freedom? This is just 1 degrees of freedom. So you, if you lock just one of them, other one becomes locked even though it is free. So number of inputs gives you number of constraints that you can apply to this type of mechanism. So over here it is 6. So 6 constraint, if you can constrain all the joints, robot becomes constrained. That means you, if you calculate the angles of all the joints with respect to the top platform location, so that fixes all the inputs. That means top platform is located the place you want it to go. Okay, so this is the philosophy of this. How it is done? Again, you do the same thing. You just calculated the linear length of the this particular distance, this vector. Okay, this is the vector, and you transform this to the base frame. Transform this to the base frame by applying the rotation matrix. How the base actuator is rotated, take it to that frame. So you know how the actuators are fitted, different angles with respect to this. So multiply with rotation matrix to this vector, you get this vector in terms of bi frame. Now you just do inverse kinematics of this 3 link manipulator. What you will get? You will get the angle. Once you get that angle, you are done. So one by one you can get all the angles because you know all the top platform locations. So this is how it is done. So I'll skip most of the things now. This shows what? This shows the orientation of motor frames. This is how it is connected. Okay, so this is the angle with respect to the base center frame. Okay, and then I am just doing the inverse kinematics of that particular joint. So what it shows? It shows the second joint. Basically this one is 2 degrees of freedom. End point is here. Okay, so I'll just skip this one. If somebody is interested, can just take snapshot of these screens. Okay, and finally system control integration. What is this system control integration? Over here what we do, just take input as a position trajectory that goes to the inverse kinematics solution of this particular robot which I want to control. That will give you the joint angles. So that becomes the input to the actuator. Now whole of this is inside this actuator. So what happens? So any angle as actual angle which the actuators are giving you is fed back to the controller. Compared to the desired angle, error goes to the PID controller. Yes, there is PID controller inside. That goes to the actuators. There. Okay, and actuators gives you an angle. Additionally, it also can give you feedback of joint angle. Each angle basically goes to a torque limiter over here. In my algorithm it is there. I take input of the, yesterday you just saw what is torque compliant robot. So what happens, for each angle I wanted to know how much would be the torque required for a particular joint to be there. So that torque was calculated and that particular limit was set. So this basically is not always there. That is because I wanted to make this robot compliant, so it is there. Okay. So this is what is the control integration of whole of the system. The one which the video I'll show, it uses standard motors, servo motors, not the standard though, these are little expensive ones, which are known as dynamic cell servos. So it uses ARM Cortex M3 processor, 32-bit. So you have a high valued analog inputs for to sense the joint angles, contactless absolute encoders, as it says, it is 12-bit encoders. It has Maxon motors, which are one of the best in the market with PIDs. So it gives you something around 8000 bps to 4.5 mbps speed over serial TTL communication. So that is one of the beauty of it. I need to control everything in real time. Okay, so that is the reason I wanted to have a huge a large communication speed. So this gives me that through TTL, USB to TTL conversion. Gear torque is good, reasonably good, 200:1, which lets you backdrive your system also. 6 Newton meter is quite high of a torque for this type of motor with 12 volts. It has both position velocity as feedback. It gives me the values of both load also, error and voltage if it is going well or not. Compact, these are very compact, lightweight, and you can have them in daisy chain. Just 3 wires needs to go from first motor to 253rd motor, that is 0 to 253. Total 254 motors can be there. Okay, wheel or a joint mode, both it is possible through this type of motor. Wheel mode means it can continuously run. Joint mode means you can just command for some angle. Allows adjusting controller gains. That is again very good thing about this type of motor. If you are not happy with the PID gains which are set by as default, you can adjust those gains. Okay. So this is how it was connected. From USB I had a Robotics USB to TTL connector. So this TTL goes to first motor and second motor, third motor, and so on, so forth. And SMPS 12 volt can also be given. So where did I get this SMPS 12 volt? It is standard computer PC can give you 12 volt. It is a very good supply, I tell you. 12 volt, if you want, you can use just off the shelf PC's SMPS. It has something around 25 ampere capacity at 5 volt at least. That depends on the wattage of that. So you just need to connect 2 wires over here. This one can be connected anywhere along the chain. Okay, power can be given anywhere along the chain. Okay, so this is how a half duplex communication works. Half duplex is, as I have said, it communicates just through 2 wires. So how one is common, that is ground. Data is to and fro. Sometimes it reads the data from the same wire, sometimes it sends the data from the same wire. This is what is half duplex. It is done like this. Standard IC something like this is there. So this is already there in this type of devices, U2 D2. Okay, so that is used to communicate this type of devices to these motors. Okay, so now again I'll show you some video demonstration of different application of the simulator of different this type of actuator, that robot that we have made. Okay, so I'll just switch it on now. Okay, one of the very popular application which most of you must be seeking is a control application. When you want to control, when you want to teach your student some control thing, that means you want to teach your student a bidirectional control is used over here. So what is at the top is nothing but a touch screen, resistive touch screen, and a steel ball can give you enough of an impact to measure the position of that particular ball. So it was integrated using a standard Arduino. So it gave me some exact position of this. So that gave me the feedback of the XY of this particular ball wherever it is lying. Somebody can go use top camera for this reason, and they can identify where the ball is with respect to this top platform. So that also is doable if you don't know where to get this resistive touch screen. So at the bottom I have just this platform. So roll and pitch motion was used to control the location of this ball. So you see, I can precisely make it go anywhere in this top platform. Any XY location I can command, any trajectory also I can command. So these are the two examples. Got it? So what additionally I had is a accelerometer which is fitted down below. So it is not exactly this platform, but you see there are accelerometers which gave me a live feedback of where it is located. Okay. This yesterday you must have seen Aditya giving a talk. Hopefully that is what is a Neogenics. This was developed by us. Later on it is getting sold by Aditya through his company. So what you see here, it shows you all the capability of a 6RS platform again, but this time it is made in a different way. You see, top and bottom platforms are hollow in shape. It is made just in a way similar to a special tailor frame for one of the medical application. So this is the GUI and the coding environment that is very much like a Python, which can be used to control this. So what you see now, it is getting load tested with 5 kg payload, almost 4 kg plus this wooden weight and 0.5 kg additional. So this type of load testing we did to check what would be the behavior of this particular platform. So this is exactly 5 kg plus. So this is how it was tested for load. So if it is designed for 5 kg, it should work for 5 kg. This is the extent of parallel robotics work that we are doing. So I would just skip this. So tool frame location is very interesting. You can maintain one of the position fixed and move rest of the motion. Yesterday you just saw one of the cobot doing this, right? Arbitrary frame you can fix, okay, and you can rotate whole of the platform with respect to that particular point. That is very useful in case of medical applications. So I have set a different tool frame now, which is getting stationary. Okay, so these are some of the tests. Now this the front one is stationary now. You can see. These are beautiful motions that you can give if you know how to do the transformations. Okay, this is a speed test. Just 10% speed is this. So anyway, I'll go forward with the next one. So again, I used a parallel robot to do the thing which I have done with the cobot yesterday. So I showed you inserting a pallet in a hole, okay, through a spiral search motion. This can be done with a serial parallel combination. So that is what we did. Over here I have just attached a parallel robot on top of a serial robot. This is for micro manipulation, as I have said, and this is doable. You can fit a parallel robot on top of a serial robot. So this lets you what? This lets you giving a micro motion apart from what a serial robot can give you, a huge distance motion. Okay, so I am just checking the repeatability with this, if it is possible, what spiral path I want to cover and how is it going. Okay, so I have just compared the spiral paths because I wanted to do peg in a hole insertion. So yes, it can do, you see, even without a cobot with compliant. That is the reason I made this particular joints compliant. Okay, and then it can do same type of peg and hole task in no time. It is even better than the one which was done by the cobot. Okay, so this is one of the example assembly tasks getting done by a serial parallel combination. So this is some of the application of this parallel robot. Okay, going to next, how does our simulator is simulator looks like. So it looks like this. We have different controls, we have exact configuration how a robot goes in a real time. It gives me a live feedback over here with different plots of interest. So because it is developed through academicians, not through any industry, it has all sorts of features, parameters visible which are intrinsic most of the time with any industrial robot. So over here we did it through because of some academic interest. So I am showing homogeneous transformation matrix, joint angles live, commanded, and the actual positions where it goes, different type of trajectories, Lessages, serial, spiral. Okay, so all different standard trajectories we did it. It can move in end effector Cartesian frame, and I can make any of the tool frame stationary. So these are some of the capabilities which was demonstrated using this GUI tool, which can be used by any academician to teach their students, right, do any particular research. Okay, so this is all about this GUI. It shows you all the kinematic points also. Okay, I'll go to the next. So this is one of the application when most of you must be will find very interesting, because just like this, exactly this platform I have used, okay, to do this particular task. Okay, so what it is doing, it is simply measuring the location of this top platform, orientation of this top platform when I am moving it, okay, through this bottom accelerometer. Robotics club member and very hobbyists must be knowing this, how it is happening. You must be thinking this is glued on top, but actually it is not. Okay, it has moved a bit now. Okay, so this is one of the application which is known as a balancing or uh, noise cancellation, low frequency noise cancellation. So this is one of the application. Flight simulator, flight gear, if you know, it is integrated to that flight gear. So this is the flight gear front end which is integrated to a parallel robot of this kind. Okay. So it can simulate constant running, landing, takeoff, everything. So this is done. Okay, so altogether different applications I have shown you for 6 RSS hardware. Okay, that we have built it as a product now. So pedagogy in robotics using parallel robot, yes, it is possible or not, that is what I wanted to discuss. As an alternative with current curriculum, is it possible? Almost all the things which a serial robot can do, this can be done with a parallel robot as well. Okay, so you can demonstrate all the applications because it can go to any XYZ location. Yes, or any orientation. Definitely you can do pick and place task, you can do vision based control, you can do any programming thing that you were doing with your serial robot. You can teach your student transformations because the sources are open. You get access to the intrinsic parameters. So what you see here is again creating arbitrary reference can also be done. Just now you have seen that demonstration. Now that you know the link length, different parameters, where your joints are, how it is located, how it is oriented, so you know each and every parameters, those geometrical informations, because it is made in India, we know each and everything, we do share that. You can easily do that. Okay, so creating an arbitrary reference requires precise information of those parameters, so that is what is easily available. Tool center point and base stitching, what is that? When you buy a new robot, you don't know, uh, you just know the flange location. Okay, so robot tells you by default where is your flange located, flange center is located with respect to the robot base. But as soon as you attach any tool, so what happens? The coordinate changes, the end effector location changes. So that is the tool center, and that can be calibrated even with this. Base stitching can be done. You can have different orientation of the plane workspace where you want to go, okay, where you are operating. So that orientation can also be known with respect to the robot base. So these things can easily be done, which you have been doing with standard industrial robot. Forward kinematics, yes, it is difficult, but in isolated cases, definitely it can be done for simple parallel robots like a pantograph mechanism or a 4-bar mechanism like this. Okay, inverse kinematics, yes, you can do in no time. Forward kinematics definitely is a research problem. Yes, you should take care of that. You should start doing that because it is a research problem. Research is not yet over in that. Singularity, those issues are there. That is for research students to know. Okay, and inverse kinematics, yes, you can do it for complex mechanism even like this. Uh, we have done it and it is easily doable. Trajectory planning, it is doable here also. You can do Cartesian trajectory, you can do joint trajectory. Control systems, everything is open. You can design your own control system. Even the actuator PID can be edited. Okay, hardware integration with any external sensors, because the system is now a PC based control, so you can easily integrate many other sensors to your robot. Okay, robot programming, it is there in Python. It can be done in LabVIEW, MATLAB, because the actuator supports working with ROS and different environment. Definitely it is also supported by the robot because it uses that particular actuator. Advanced applications uses a medical application. Okay, a medical application or any simulator, if you want to make, you can definitely work on that. Okay, as you have seen, I was doing some flight simulator and a car simulator that I have made. So these are 11 different tasks. That is not an exhaustive one that I have noted here. That can easily be done. So all sorts of things which you have been doing with a current serial robot, you can easily do with this. This also has an IoT based system. Okay, an IoT based system which can be communicated to any cloud server. All the data runtime values can be communicated there. Even with that, we can give you the data back. I'll show you the demo here again. Okay, so the earlier platform we named it as Santulan, and this one is, we call it Arun. Then, so what all things you saw just now is it has controller with the GUI that you have seen, joystick, fully enclosed cell and a gripper, two-fingered gripper, 6 RSS parallel platform. So it has a planned trajectory, as KUKA also can do. KUKA LBR robot we are doing. It gives you Lissajous motion, a precision based task. These are useful while you do any search task. Okay, search trajectory. This is pick and place, picking up a pallet and inserting to a hole. So you can have a camera integration also. We have done that. IoT support, using that you can control this robot using any mobile device, and you can get the feedback also. Current position of the robot can be obtained over here also. Can be moved with a joystick, it can move with a command through different programs, Python interface, so different ways you can operate that. Got it? Okay, with that, I think I'm done with my content. So thank you all. I would have loved to talk you all in live, but unfortunately due to COVID and various occupations, I could not do that. So I would suggest you go to my channel, subscribe to that if you want to get updates on this. And definitely you can post any comment on this. You can ask any queries there. You can mail me and I'll definitely try to answer you all. That's all. Thanks a lot.